33. Oh, by the way, before I forget, last Friday, no video was taken. So that's if anybody's looking for last Friday's lecture, it will never be there. It is lost forever. Number 33, you said?
Yes.
All right, so the top of a ladder. They love sliding ladders. It's kind of funny. The top of a ladder slides down a vertical wall at a rate of that. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of that. All right, I love it. So this is kind of backwards because they're asking you how long the ladder is. They're not asking us for any rates of change because they gave us all the rates of change. So if you haven't tried this problem out yet, number 33, can you draw that picture? If you have already, just sit there and stare off in your favorite direction. Has everybody tried that one? I would hope that most of us have tried that one by now. Okay. So here we have this. Ooh, look at that. That's beautiful. So, what is in symbols? I don't know what symbols you guys chose. There's my variables that I chose. The top of the ladder slides down at a rate of 0.15. So obviously, what's 0.15? Say again? Sorry? 0.15, what is that in symbols? The top of the ladder slides down a vertical wall, rate of that. So what's 0.15? dy dt. Right, per time. Pretend like that's an S. That'll be, okay. It's not a 5. All right, let me stop for a minute. Is everybody cool with that? So a huge part of these is creating your own variables that you need, linking what you just created with the rates of change or whatever else they tell you, right? So if you chose to call this W for some crazy reason, then this would be dw dt, right? At the moment, when the bottom of the ladder is 3 meters from the wall, so the snapshot is x equals 3, it slides away from the wall at a rate of 0.2 meters per second. So, of course, what's that going to be? Yeah, dx dt is, where'd it go? 0.2 meters per second. I like it. So this one's not too bad. They wanted to give you, does everybody agree with me? Do you guys understand what you would do from here? I mean, what's the relationship between my variables and the thing that I want to know? What's the relationship between x, y, and L? What kind of triangle?
Right triangle.
So what's the relationship between x, y, and L? So when I ask you what's the relationship between variables, I want an equation answer.
X squared plus y squared.
Pythagorean theorem. I like x squared plus y squared equals L squared. Right? I like it. Now I love it. I remember, real quick. One time I was doing an algebra class and I said, if we cut a board that's 24 meters long into 3 pieces, we have to do variables for each piece. One is twice as long as the other one. You guys kind of with me? Remember those kind of problems? And the one guy in the back is like, Mr. Waller, you lose about an eighth of an inch of the wood in the teeth of the saw when you. I'm like, you can put that into your equation. The rest of us are using lasers, right? So I want you to understand: is the ground going to be perfectly flat in the real world? No. Is the building going to be perfectly straight up and down necessarily in the real world? No. Is the ladder not going to be buckling? No. So, just in case anybody...
Should add a coefficient of friction.
Say again?
Should add a coefficient of friction.
Coefficient of friction, look out, right? But that's already baked into the rates of sliding. So that part's okay. We just don't explicitly see that. Anyway, just in case you start to think about that, what we do, real quick, what we do in mathematics is we learn what would things act as if there was no friction, or we kind of assume things are perfect. And then later math is is when you start bringing in other variables, or you start allowing for imperfect stuff in your problem. That gets, the math becomes much worse. I have no idea what prompted me to go off on that, but our picture is really perfect and the real world isn't, but we're modeling the real world with pure math, right? Okay, I like it. Anyway, now that I've made you feel as if there's more to this problem than there really is, there isn't. You do exactly what you just said. You take derivatives, you throw stuff in. Yes? There is one little thing about, there's something you don't know that you're going to need to know, but I think I've said enough to at least get you started if you had any trouble with this problem. You guys, anybody had trouble with this problem? This is number 33 and 39, so this is the beginning of that problem. Okay. Anything else from homework that I can find weird things to say about? Yes?
Can we look at 3 times number 9?
All right, let's see. So verify. Oh, okay, so they give us what should be the linear approximation. They want us to verify it. So you just have to go, there's your f of x. That's a fourth root. You go through the steps, right? F of a, f prime of a. Is everybody with me? Then it says, determine the values of x for which the linear approximation is accurate to within 0.1. So there was that example that we did together, and I believe there's at least one example in the book. Is there? Yes. Right here. This is a beautiful example you could follow for the accuracy part. So this is exactly what we did together in class. Does that look at all? It wasn't this exact problem, but okay, I like it. And we had to graph it. So, I like it. Yes?
I have a question about the last problem.
Yes?
When you're finding the derivative of L, would you do DL dt or no? It's not actually changing.
Yeah, what's happening to the ladder over time? We're assuming that the ladder's length is not changing. Yes.
Is this 2L?
No, no.
0.
0. Yes. So the derivative of L squared is 0.
Okay.
Very good. What's the first thing you look for? Can I simplify? What's the second thing you look for? Is anything a constant? I like it. Because that would suck. Can you imagine if the ladder itself was also like collapsing? This is what I mean. That would be a whole other level of shit to worry about. Oh my God. Okay. All right. Anything else from homework stuff? Okay. All right. So, last time we talked about, I think we did mean value theorem last time. So I'm going to let you guys try some of those out, see what you think. We're going to get into extending our understanding about what calculus tells us about the shape of a graph of a function. So we already know some basic stuff. Somebody help me out. If I'm given a function, what can we determine from f prime?
That is really boring.
Holy crap. Okay, let's see what happens. Is it because I did this? I don't know. What can we determine about f of x from f prime? I love how open that question is. Give me anything. If you're given a function and you take the derivative, what can you then do with that derivative to figure something out about the original function? What does the derivative tell you? So look, okay, so let me ask you this again. Given a function, we take a derivative and then we do some shit with the derivative. What could I determine about the original function by messing with its derivative. Slope at a certain point, I love it, right? So that's the very first thing we did. All right, now kind of zoom out a little bit. Horizontal tangents, which would lead to where the function is. All right, no, careful. When I say the function, that's f of x. So if I find horizontal tangents, how do we do that? What do we do to find the horizontal tangents? We set the derivative equal to 0, right? This will help me determine what type of points? Critical points. And what are the critical points? Those are locations where what might happen? Possible local, max, min. What else besides equal to 0 could lead to that? Good Lord, Jeff. Undefined. I like it. There's a hidden E in there somewhere. Let me stop for a minute. Okay, I like it, right? Anything else sort of less specific here, a little bit that comes off the first dude? What's the most basic thing that the derivative can tell me where the function is increasing versus decreasing, right? Which kind of leads to the turning points, which kind of leads to these things. Yes? Okay, so intervals where increasing, decreasing. Okay. Now, let me show you something. Okay. Students normally hate this kind of question, which is just kind of like, what can you do with this? And no, ask me, tell me to do something and I'll do it. Don't tell me what I could do. Let's see. Everybody ready? I'm going to switch over. All right, so this is kind of cool. I showed us something like this earlier this semester when we first talked about slope. Did everybody see that okay? You guys can see it? It almost doesn't matter what's over here. So I made a little function. Look at that beautiful little function. Aw. I put a little 0.07 just to scale it down, because otherwise the max and mins are going to be way off the screen. It's going to be kind of huge. So can somebody tell me what it looks like is happening here? I mean, obviously, what is this red line? Tangent line. I love it. What is this red point? What the shit is up with that little red point there? What do you think? I'm not sure. What did?
The reflection of it?
Not the reflection, no. Yeah, it's the slope at that point. So as I slide along, what should be a slope be right there, of course?
0.
Look what the red dot does. And real quick, what's the slope right here? Really big, positive, until it gets to about right here, right? So watch the red dot. It's going to go big, positive, and then it's going to come back down to 0. Okay, I like it. Stay with me. So back in section 2.8, you basically had to be the red dot. They gave you a function. You had to graph what the derivative would look like even before we really knew how to do a derivative, right? Which, I loved. So now watch this. Let me turn this dude on. Bam! Look at that. That's the thing it's tracing out, of course, right? That black curve, what is that black curve? Derivative. So the black curve, if this is f of x, the black one is f prime of x. Okay, I like it. So this is old shit, right? This is old stuff. If I go to where there's a maximum here, just about, then my black curve should go through 0. And it does. Yay. Okay, now we're going to talk about the next level of this. Let me take that derivative away. Now what I want you to do is to consider this. The derivative tells me what the function is doing, right? If the derivative is big positive, the function has got a huge positive slope, yes? If the derivative is small positive, then it's got a small positive slope, so forth. Okay, we know all that stuff. What would it mean? What would a second derivative tell me? So tell me this. As I move, how is the slope itself changing? So right here, where's the slope changing by a lot? And where is it not changing by much at all? Like, let me ask you this. Is the slope right here is big time negative, yes? Is the slope getting bigger or smaller as it goes around this? Bigger. Yes? And then as I go up here, what's happening to the slope now as I round this turn? It is now getting more positive, yes? But then right here, roughly, there's something interesting right in there. I want you to really, I don't know if you guys can really see this. Okay. See how the red line is, the slope is increasing on the red line? Which means the first derivative is increasing as I move along. Does that continue, or does it change somewhere?
It changes.
So here it's getting more steep, it's getting bigger, and then about right there, so right there it's getting more steep, and then about right there, somewhere in here, it's getting less steep now. Until, of course, the slope itself goes to 0 over here somewhere. Okay, so as I come through here, the slope itself is getting bigger. Until it gets to about right in here somewhere, it is the biggest positive it's going to be for a while, because then it starts to decrease again, of course. Okay, maybe. So, in fact, let's keep going. I want to get around one of these, this guy up here. Now what's happening to the slope? It's decreasing now, right? And it's decreasing until right in here somewhere, yes? Because now it's starting to increase again. Okay, so the slope of the slope. Oh shit. The rate of change of the slope. That's the second derivative, right? Any derivative of any function is the rate of change of that function. F prime is the slope function. So F double prime is the rate of change of the slope function. So how is the slope changing as I move along the curve? Well, it's getting more positive here, and then it's getting more negative here, right? Okay, so let me see. I don't know if this is going to translate as well. We'll find out. All right, Jeff, let's see. I've added some more shit onto here. Let me see. What do I want to turn off? All right, give me just a minute here. Okay, let's do this. And let me turn these off. I think, yes. Hold on to your butts. Okay. So now as I move around, let's see if this makes any sense. That green line represents how my slope is changing. So right in here, my slope is not, somewhere in between there. I really desperately want this to make sense, but this is really weird. Everybody agrees with me the slope is getting much bigger around this curve, right?
Yeah.
Right around here somewhere, the slope is not changing much. And then the slope is getting more negative. Okay, so let me just stop playing with this. This is not going to do exactly what I wanted to do. The second derivative ends up telling me how it's curving. If it's going, let me see, here we go. Okay. So if I have, let's do this. I like it. Okay, let's do something more specific. So let's say I have a function, it's at A and B. This feels like we're going to do mean value or some weird shit or Rolle's theorem or something. I sort of pointed this out when we talked about those theorems. How could I connect those 2 points in a continuous fashion? I could just go straight between them, yes? Would you all agree that's the least interesting way to do that? Right? Okay. So that's sort of like the least in. Or I could do this, yes? Or I could do this. Now, of course, I could do a lot of wobbles in between, but I don't want to. I've kind of zoomed into the one wobble, whatever my big function looks like. I've zoomed into one wobble. Does that make sense? One wobble. Okay. This would be like, have you ever heard in the news, the unemployment rate, the rate at which unemployment is increasing is going down. The rate at which unemployment is increasing is going down. And would you agree that represents this? Isn't this increasing? But the rate at which is increasing, is that what is happening to the rate at which it's increasing? It's decreasing. Okay, I like it. So that would be a situation where the second derivative, what do you guys think about the second derivative? What's happening to the slope as I move? It's getting smaller. So this would be a situation where the second derivative is negative. The change in the slope as you move is negative because it's getting smaller. So think about it. I really want this to make, when I look at a function, if I move and it's going up, doesn't that mean the first derivative is positive? Yes, I love it. Because the function itself is increasing. Here, what's the slope doing? The slope is getting less. Therefore, the rate of change of the slope must be negative. So the second derivative must be negative. So what's true about this guy? So over time, the slope is getting bigger. Therefore, this has got to be positive. Okay, let's let that sink in a little bit. So the second derivative is kind of like 2 steps removed, right, from the original function. That's why it's a little bit harder to conceptualize, because it's 2 steps removed. You're not thinking about the function itself. You're thinking about what the slope is doing. So let me ask you this. What if I had these two? Jeff. A little bit bad, but that's all right. In both of these situations, what's true about f prime across most of this region? What's true about f prime? It's negative for sure, because the function itself is decreasing in both situations, right? If this was profit of a company, which one would you rather be seeing? I'd rather see the first one if I had to pick from one of these two, right? Of course you go, I'd rather this be going up. But if you had to choose between these, I'd much rather look at the one that looks like maybe my profit is stabilizing. This one looks like, okay, shit, right? Okay, maybe. Which one of these, all right, let me ask you this way. What's the second derivative for this one across A and B? Yeah, this one's getting more, the slope is increasing, correct? So this is positive, and this one is, got to be the opposite. The slope is getting smaller as I move, therefore the rate of change of the slope itself must be negative. Okay. I like it. I keep hammering home the same idea because I really want you to connect with the second derivative as much as I believe most of you are connected with the first. I think the first derivative right now, you all feel pretty comfortable about it, right? Okay. So what does this mean? So what this means is, if I see a function, let me ask you this. If I see a function like this, okay, can somebody broadly tell me where the second derivative is negative? Let me give us some points here. Okay. Where's the second derivative negative? A to B. Because what's the second derivative of negative mean? It means the rate of change of slope is decreasing, which means the slope itself should be decreasing. And that's exactly what's happening all along here. And why did I pick B? What's special about B? That's a little too far ahead.
Sorry.
Don't use terminology yet. What's true about the point B? What's happening at B? The slope is decreasing all the way, but then right at B, what starts to happen? Starts to increase. So what do you think the second derivative at B is? It's got to be 0. Same way as this. My function's increasing. The first derivative is positive. My function's decreasing. The first derivative is negative, which means right in the middle, it's got to be 0. It's the same damn thing. So what, if I can look at first derivative telling me increase, decrease, what's the quick way to think about second derivative then? The quick way to think about second derivative is cup down, cup up. Frowny face, happy, whatever the shit, right? So this whole region here, F double prime, is negative. This whole region here, F double prime, is positive. I kind of had a little overlap there, too bad for me. Does that make sense? Cup down, cup up. Holds water, doesn't hold water. Is another way to think about it, right? Okay, so before today, we didn't necessarily know how to connect 2 points with the correct curve. Now we do, unfortunately. It's just going to be another step in the process of figuring out how to graph something. I'm going to have to graph the curvature correctly, which means when you guys answer a homework, quiz, or test question, I am going to have to be really anal about when you connect things that there's no wobble in there, because that would mean that you should have found weird shit happening with your derivatives. Yes? So if you're supposed to be cup down and you do something like this, see that shit? Oh, Jeff. Oh, that's so picky. I don't care. Because what I'm going to need to see from you is, are you able to do the derivatives? Are you able to find the critical points? And then are you able to translate that into the visual? And if there's a disconnect anywhere, you haven't shown me that you know what that means. Okay. Now, I'm not going to be so evil that I'm going to look at it with a magnifying glass. But you can't let little things like this happen if they're not supposed to. Okay, maybe. All right, so what the shit is this thing going to look like, Jeff? I don't know. Let's formalize a couple things. All right. What if I had this? If I had taken my first derivative and I got here. Can you guys right now just do what you need to do to figure out where there's a max and a min? If there's any local maxes, local mins, can you guys do that work? And just in case, what am I going to draw to help me do that work? What are the critical points? Or critical numbers, let's say.
0, 1, and 3.
Yeah. And then what do I draw to help me visualize this? Just the number line. Right, so go ahead and do that work to figure out where the local maxes and mins might be. Is anyone thinking about multiplicities? What are you guys doing? I see you guys doing stuff. Can somebody tell me what you're doing? Yes.
I'm plugging in -3 to figure out whether or not the lowest one is positive or negative, and then.
Well, you can't plug -3 in because I know that's going to give me a 0, right?
-4.
Okay,
Or
-4.
Anything past it.
I love it.
And then if it's to the first power, it punches through, and if it's an odd, it punches through. If it's an even, it bounces.
Ooh, I like it. Punches through and bounces. I like a one punch. So, what I really want to know is, what is the sign of this at -4? So this is always positive, right?
Yeah.
I can kind of ignore this guy. He's always positive. This will be negative. This will be negative. So down here, positive. Which means what's the function doing up till -3?
Going up.
Increasing. I love it. Now, what's got to happen here? I don't have to do any work. Where did -3 come from? It came from a piece that was an odd power. So what's got to happen here? It's got to change signs. Multiplicity is 1. It's got to punch through. Therefore, it's got to change signs. What's going to happen at 0?
Same sign.
Stay the same. X squared bounces. So if it was negative to begin with, it's going to be negative again after. This is the power of multiplicity. And of course, what's going to happen over here? Positive. So then you could answer questions like, what intervals is the function increasing? On what intervals decreasing? Is there a maximum? A local max? Yeah, so there's a local max in -3. Because it goes, in fact, I always forget. So you could, if you want to, you could kind of graph yourself a little. So it's up and then it's down, flat, up. All right, that's horrific. It's too bad, Jeff. So at 1, there's a local min because it goes down to it and then up from it. Okay, I like it. Okay, that's all stuff we've done before. That is officially called the first derivative test. So if in the homework they ask you to find the local maxes and mins using the first derivative test, this is what they mean. This kind of implies that there's going to be a what? Second derivative test. Okay. So let's talk about that. What is the second derivative of this function? Let's see if you haven't written it down. There it is. Calculate the second derivative of this. It's going to be exciting. So I get that, doing it real quick. So derivative of x squared, other two stay the same. X squared, derivative of the middle is 1. X squared, the middle derivative of the last guy is 1. Is that? What's the only thing I can take out of that? Can I take an x plus 3 out? Can I take an x plus 3 out? No, because this guy doesn't have. What about x? Shit. So the only thing I can take out is an x. So then I've got, let's see if we can do this. 2 times x squared plus 2x minus 3 plus x squared plus 3x plus x squared minus x. Okay, let's see if you guys are cool with that. Kind of skipped a step there. Is that all right? Took an x out, and then I just distributed stuff. Let me get my like terms together. Let's see, 2x squared is 4x squared. Then I get 4x, 7x, 6x. And then I get negative 6. Wow, that looks gross. Now, all I want to do with this, for this moment, is to show you what the second derivative test looks like. And then we'll do some more stuff with the second derivative. Let me ask you this. All right. Let me see if you guys are cool with this. So everybody's got this here, right? Okay, hold on to this for a second. Let's talk about an idea. If I have, okay. If I have a function and, what do I want to say here? Okay. If the function is got a second derivative greater than 0, what does that mean it looks like? No. Cup up, right? Cup up. If there's a critical point, if the second derivative at a critical point is greater than 0, what's true about that critical point? It is the location of a minimum. So if I'm cup up through a whole region and there's a critical point in there, it must be the minimum. So this is what the second derivative test is. It says, I don't want to draw that stupid number line. No, I want to take a second derivative, and if it's cup up, it's a min. If it's cup down, it's a max. Is it always cup up or cup down? What could it be otherwise? Indeterminate, because it could be f double prime is equal to 0, which means I don't know. Okay, maybe. So coming back. Okay, let me say this. Is everybody cool with this idea right here? If it's cup up and I have a critical point there, it's got to be a minimum. Otherwise, like this, right? It only doesn't work if the second derivative is 0, because then I don't know what's happening there. So watch this. Let me see if I can bring this back together. I've given myself no room for all of this. We already determined the answers here. But let's see if we can do it again with the second derivative. So look at my critical points. 0, 1, negative 3. So let's do negative 3 first. What's the second derivative at negative 3? I don't even care about the actual number, but let's see. Negative 3 times 36 minus 18 minus 6. Is this positive or negative? Positive. So negative times positive. So what's going to be true at negative 3? That's going to be a location of a what? This means it's cup what? Sorry. Where'd it go? Work with me, paper. Oh, the bane of my existence is paper. Okay. It's cup down. So what's going to be true at negative 3? It's going to be a location of a maximum. Isn't that what we got? Right? And of course, what if we try 1? If we try 1, so then I get 1 times 4 plus 6 minus 6. 1 times 4 is positive. So therefore, that's cup up, which means there should be a cup up. There should be a minimum there. I know it's a little counterintuitive, but you got to realize if it's cup up, that means there must be a valley. There must be a lowest point. And is that what we discovered here? Yes. And what about at 0? Oh, shit. What's true at 0? It's equal to frickin' 0. That means the second derivative doesn't tell me shit. Okay, let me stop for a minute. So I want you to understand this. Second derivative test is valid. Will it always give me the answers? Did we get an answer for 0? Do we know what's happening at 0 just by the second derivative test? No. So I agree with somebody who's sitting there saying, why would I do the second derivative test, right? Because it doesn't always give me an answer. Plus, Have we done functions that you're like, thank God I don't have to do another derivative? Have you guys done a derivative and looked at your answer and went, thank God I don't have to do anything with that? Are you with me?
Yes.
Isn't the second derivative often enough going to be kind of gruesome? Okay. So there are a couple of things at least going against using second derivative all the time. But it's good to know it exists and what it means. So you are going to see homework that forces you to do it. And of course, you're going to see me ask you to do it too on a test. But normally I'm going to give you a function that's not going to be too insane. Of course, you're like, what's your definition of too insane, Jeff? Well, you got somewhat of an idea of that. Is everybody okay with this so far? I mean, this is kind of beautiful. First derivative is increasing, decreasing. It's the shape of the function. It's whether the function itself is moving up and down. Second derivative is more about the shape. Second derivative is about cup down versus cup up. What are the most important kind of points from the first derivative would be the critical points, yes? And what happens at a critical point? That could be a max or a min. So we're finally catching up to what you said earlier. What's the most important points for the second derivative would be the same idea, would be its critical points. What could happen at the critical, so let me ask you this. What happens at the critical point for a first derivative? It could be going up and now it's going down. So the critical point is the place where it changes from increasing to decreasing, right? Or decreasing to increasing. Or it could be just taking a rest for a second. Okay, I like it, maybe. So the second derivative, if the second derivative is all about cup down versus cup up, what's happening right at the place where it's 0 should be where it's, on one side it's cup down, for example, on the other side it might be cup up, right? And we've seen a freaking, like, cubes are huge for this, right? Good old Loch Ness Monster curves. There's going to be that place where it's a hump up and then a hump down, right? Or the other way around. You guys are with me? You guys sort of with me? All right. So first derivative critical points are where one side could be increasing, decreasing, and then it changes, maybe. Second derivative critical points, one side it's cup up, cup down, and the other side it might change. So again, the critical points for either one is possible locations of the function changing behavior. I understand I just said behavior weird. Behavior. Okay. I really don't know if you guys are with me. All right. So, I've run out of paper there. Need more paper. There's more paper here. Oh, that's not what I need. So what we call this position, what we call this thing for the second derivative, so the second derivative equal to 0 or the second derivative undefined are the critical numbers for the second derivative and are possible locations for a change in, I haven't said this word yet, concavity. Let me make that an I for sure. So the real word, not just cup up, cup down, but the real word is concave down, concave up. Okay, I like it. I sort of primed you for this because some of you guys have heard of convex lenses versus concave lenses. So we just decided to always call it concave, and it's just pointing one direction or the other. Okay, all right. All right. And what we call, if the concavity does change, good Lord, Jeff. At a point, we call that the inflection point. Good Lord and a half. No, I don't know what language letter this is, all right? Let's see, inflection point, there we go. Sorry? So it's kind of like just one level up from finding critical points in local max and min, the next level up you find critical points the exact same way, just for the next derivative up. And then it's got its own terminology because it's a second derivative. It's not going to tell you the same thing the first derivative does. All right, so what is this going to look like for us, Jeff? Okay, so let's do this. I'm actually going to do, let's do number 2. Let's do the one on the back together first. And then I'm going to have you do the one on the front yourself. The one on the back is a little more complicated. Let's look at this guy. What is the most important first step on number 2? I mean, find a domain. Okay, I've got to do that. So can we just find the domain? What's the domain of that function? Yeah. Got a couple square roots. I need the inside to be positive or 0, so there you go. Now, before I do part B, what should I do with that function? Yeah, rewrite it. And again, I think I've said this to you guys, that we should have never invented radical notation. It really should never have been invented. Seriously. So, here's what kind of makes me cry, is when somebody rewrites something like the first thing as x to the 2/3. That makes me cry. Of course, I love the face you're making. I love it. No, okay, that's the exact same face I make when I see somebody do that. What goes on the bottom always for radicals? If I'm going to rewrite them as a fractional power, what's on the bottom? Roots, just like on the bottom of plants. Roots on the bottom, power on the top. So that'll be 3/2, right? And then this will be minus 3x to the... Yeah, be careful. See that? Is everybody cool with that? That 3 is obviously not the root. You guys see that? So I can't do much about that. If you ever see a test or a quiz and you're like, I don't know, just come up and ask me, right? Before you start doing the problem. So take a minute and see if you can verify this. And let me see if I can verify it and make sure past Jeff wasn't on something. Let's see. When he did this. Yay! Just to kind of prime you for this, because I don't think we've done this specifically. If you're having any trouble factoring it, how do you factor this? Get out of there. How would you factor this? Pull out x to the 4th, right? Why? Yeah. And so what's the shortcut? You always look through and find the what? Like if I had this. What do I pull out? X. Why? What's the quick shortcut? Find the one that has the smallest power. 11. That doesn't change. That never changes. You find the one with the smallest power and you take that out. He took it out. So what's this derivative look like? Derivative of this is nice, right? And then what happens here? Let's see. Right, the 1/2 comes down. the power becomes what?
Negative 1/2.
-1/2. I love it. So of course everybody agrees you can take a 3/2 out. That's in your face. What else do you take out? X to the -1/2, because that's the smaller power. Now you got to understand what the shit. What is x to the 1/2 divided by x to the -1/2? X. I love it. That's it, right? In fact, really quick, when you do this, don't you just subtract? Get out of there, Jeff. Don't you just subtract what you just took out from the power that's there? So if you take a negative out, you're actually adding that. All right. And of course, I took this out from itself, which leaves me a 1. So I verified that if Jeff was on anything, it didn't affect him enough to mess up this derivative. Yes? Because they both have a 3/2. Right? The numbers are just, they always act the same way. Yeah, you're good. You're good. All right, do part C. Do part C. Yes?
I'm confused at how you got the 3/2 on
Where did I put my little... Okay, here's my work. 3/2 comes down. Power goes down by 1, right?
the x to the 1/3 though?
Why?
Oh, I see that. Oh. I thought that was like I don't know why I thought that was like the degree in front of the square root.
Oh, this guy.
No, I meant for the first one. I thought that 3 for some reason was like on the outside.
Oh, I see. Oops. Be careful. Understood. So this should be pretty quick. How many critical numbers do you get? 2, exactly. One of them is what makes the first derivative 0, which gives you 1, and the other one's what makes it undefined, which is 0. So when I do this, I'm going to put my 0, I'm going to put my 1, I'm going to put a z on top of 1 and a u on top of 0. Just to remind myself, it's undefined at 0, yes?
If you have, I know it's not a coefficient because there's an x there, but like we're going to call it that for the sake of being separated from the other parentheses.
Sure.
You set all of the binomials or whatever's in the parentheses equal to 0. Yes. Does that mean that whatever's in front of all of the binomials, will that always give you a 0 as a critical point?
Trying to understand. Oh,
Does that make sense? Like
No, because okay, real quick. Let me make sure I understand your question.
Okay.
If it would have been this instead, so I just replaced the x with an x plus 2, right?
Yeah.
So there, the critical number would have been 1 and
-2.
yes, okay.
So 3/2 wouldn't.
Oh, this.
Yeah.
That doesn't
That's
do
what
shit.
I'm at, exactly.
Yeah, the little 3/2. So the parts that have an x in them are parts I can control.
Okay.
3/2 I can't. 3/2 is legitimately.
Right.
But if I make part of it 0, then 3/2 is dead. Right?
But if it was 3/2 x, then there would be
Ah.
a 0 critical point.
Yeah, of course.
Okay.
Yeah.
Okay.
But again, it's not because of the 3/2 at all. Numbers, I don't give a shit about.
No, of course, yeah.
So if it was this, I still would have looked at it basically the same way. Screw this guy. I get an answer from him. I get an answer from him. I get an answer from him. I'm just going to ignore the one that doesn't give me anything.
Right.
Yeah. Okay. So, very quickly, do I care about this region? I told myself I don't already, correct? My original function doesn't even exist down there. So I can ignore this whole region here. So what about between 0 and 1? Things get a little freakier because don't we have a multiplicity of -1/2 now? In a sort of way? Not really. There's a way you can look at it, but how can I investigate between 0 and 1? Put a 1/2 in there. I would put a 1/4 in there just because I'm crazy. Because 1/4 to the -1/2 would be +2. Isn't this always going to be positive? Let me stop for a minute. Is that cool, everybody? on its domain is going to always be positive. So basically, it's all about this guy. So anything below 1 is going to be negative. Anything above 1 is going to be positive. Okay, maybe. That's why the very first thing you should do in every one of these problems is look at the domain. Because then you know what not to worry about on your number line. Okay, and you don't have to do this. I might sometimes ask for this, I don't know. But basically, what does this mean, the fact that it's undefined? It probably means it's got an infinite slope there, right? So it's got kind of, and then it's going down, and then it stops, and then it's going up. So it should look something like that. And again, that's a rough sketch, who knows? In fact, do I have my concavity correct? I don't know, because this is just a first derivative kind of thing. But what does this do for me? Is there a max?
No.
No. Is there a local min? Yeah. So what's that going to be? What's the point? 1. Where are you going to put 1 to figure out where the local min is? Into the original function, 11. That always tells me where the function is. So, of course, 1 is beautiful. I get 1 minus 3. Holy shit. Okay. This is all old news, correct? You guys, well, semi-old news. This is new, but it's older than anything we're doing at the moment. All right. Verify this. Some of you guys might have already done this. I don't know, because it took too long. Where's my stuff? Oh, here we go. I like it. Okay. Let's speed this along. Everybody got that? Here's what I did. I want you to realize something. Do you have to start here? No, I could start here, right? Isn't that before we factored it? Because then I could just do this derivative, that derivative, and then factor it. Or you could do product rule on this thing. Are you with me? We're the humans. We can decide, I don't want to do it after I factor. Let me do it before I factored it, because they're both the same thing. And then I don't have to do product rule. Although product rule here is not really that horrible, but okay. So that's verified. Let me know if that didn't work out. Yes? Are you good? Okay. What are the critical numbers then? What's interesting about this? What are the critical numbers? What do you get?
Zero, -1.
Yeah, what's weird about one of those?
It's the same as the first.
No. Good. Which one of these do I have to throw out? This guy, because it's not of the domain. I like it. Hey, Mikey. Okay. So do you see how the domain kind of creeps in to this whole thing? That's why it's the very first thing you do, and you keep kind of looking back at it. Keep yourself straight so you don't invent critical points somewhere. Okay, I like it. All right, so let's see. Oh, one thing I forgot up here. Come back to part D real quick. I always forget this. It's sort of like an afterthought anyway. So obviously it's increasing from 1 to infinity, and it's decreasing from 0 to 1. Okay. I just forgot to write that down. And so what's happening here, I'm going to make Sign diagram. What's kind of weird about this is my critical number for the second derivative is 0, but 0 is where everything starts, right? You guys agree with me? So it's going to be concave up or concave down forever, which sort of matches with my little rough sketch, yes? It's my little rough sketch. Okay. In fact, what do you get when you plug anything in to the second derivative? What do you get? I want to investigate when is it negative, when is it positive. I really want you to understand this is a little bit weird. My only critical number is 0. The only side I care about is this side. So if I put anything in, yeah, that's going to be positive, and that's going to be positive. So it's always positive, which again matches with, what is this? Is this cup up or cup down, my rough little sketch? Cup up, and isn't that what it says it should be? Now be real careful. Your rough sketch is not always going to be correct curvature, but this one is actually a relatively simple function, even though it looks funky. All right, we really want everybody with me. So where is it concave down? Nowhere. And of course, where is it concave up? Well, from?
0 to 100.
I like it. So basically everywhere in this domain. Thank you. I like that. Are there any inflection points? The only possible inflection point is at the beginning, where it can't be anything on this side. Are you with me? This is maybe a little too weird of a function to start with, but too bad for us. I already did. No inflection points. No if men. Now, here's the big deal. Find intercepts. Okay, so let's find some intercepts. Can anybody tell me any intercepts here? When x is 0, what do you get? 0, right? So 0, 0 is an intercept. Are there any other intercepts? How would you find them? No. How do you find intercepts in general? Don't you factor? Yes? How do you factor this? Take out a what? Yeah, take out the lower power. 3/2 minus 1/2 is 2/2, which is 1x. So where's the other? Yeah, 3, 0. I love it. So that's all of our, and here's the one intercept, right? There's 0 and there's 3. Let me stop for a minute. I don't care how funky the function looks. Intercepts have to work the same way always. Y-intercept is when x is 0. X-intercept is when the function is 0. Okay, I like it. What I just said? Y-intercepts are when x is 0. X-intercepts are when the function is 0. I like it. Let's see. Plot and label intercepts. Yes, sir. So there's this one. There's this one. So this is 0, 0. This is 3, 0. I don't know why I said label them. It's too bad. Maxes and mins. So I got a min at 1, -2. No max. So let's see. It looks like I can just use a scale of 1. You guys with me? Scale is going to be a big question on these problems for you guys. So there's a min at 1, -2. Let me put min. All right, and let me put some stuff down here. Increasing 1 to infinity, decreasing 0 to 1, concave up. You can do it, Jeff. Can you? 0 to infinity. Okay. If you label this as a min, it will help you as you connect this. So it's got to be concave up forever, decreasing 0 to 1. That makes sense. And then increasing forever after that, through that point. So it's got to be concave up all the way through. Bam. Woohoo! Okay, so the technical details in that one were gross, but the graph itself is almost kind of too easy to showcase everything. Let's see how far we can get And of course, what do you guys? Some of you guys are going to do something which will hurt you. Do not plug this in your calculator at the beginning. If you want to check. If I'm you, I'm going to check, correct? I'm going to check my work. Don't check before you've drawn it, because you'll see something in the graphing calculator, you'll put it on this, but there's no way you would have known it from your work. Does that make any sense? So when I see way too specific things on your graph and I'm like, where the hell did you find this out? No, you're just copying that shit from the calculator. At the very end, check. And if there's anything majorly wrong, put that shit away and look over your work again. Maybe. So to me, if you make a mistake here and you show that mistake on your graph, you will lose less points. Because what's one big thing I'm checking? Can you get your work translated to the visual correctly? You don't want to lose points on that step, because that's a conceptual step that counts more to me. So if you make some dumb mistake up here, I want you to draw it down here. And if you look at your graphic calculator, I don't know what I did wrong, turn that shit in. Especially if you have no time left, right? Okay, maybe. It's when you do stuff up here and it's totally different here. So try to get as far as you can on the first side. This one should be a little bit more straightforward. By the way, don't ask about domain here, of course, because it's just a polynomial. All good. Oh. Yeah. just a little hint about. So, I mean, there's the first derivative, right? When I go to do the second derivative, I don't want to do product rule with 3 parts. So what I do is I start there and then I factor, right? So much better. You don't have to use this version, this version of it. You can start with, before you factored it, no product rule pieces. So let me catch up to you guys. Critical numbers are obviously 0, 1, -1, right? No one defined because it's a nice polynomial. So 0, -1, 1. It's 0 at each of those places. The only one that's got even multiplicity is at 0. So it's going to stay the same sign on either side of 0. So if I just put in there a billion, be positive times negative times positive. So it's negative up here. Yes? You don't have to use a billion. You can use 2. Which means, what's it going to be in here? Positive. It's got a change sign on the either side of 1 because that came from a first power. Down here it's got to be positive because it came from an even. So it came from a multiplicity 2. So it's going to stay the same sign on either side of 0. And then, of course, it's got a change sign again. So if I do a quick little, it looks like it's going down, flat, up, down. Really, really gross picture there I made, but who cares? Does not have to be perfect. So is there a min? I always forget about increase, decrease. Dadgummit. Is there a min? -1, there's definitely a min. I can see it visually there, going down, coming up, so it's got to be a min. -1 something. What do you get when you plug a -1 in? Where are you going to plug a -1 into? The original. Good. What do you get? Sorry? 12? So when you plug a -1 in, you'll get -5 plus 3. Is that cool? -5 plus 3, so -2. And what's the max? Yeah, 1, and of course that'll be 2. I like it. It's always nice. Increasing. Can I say increasing from -1 to 1? No. Why? Yeah, at 0, is it increasing? No. It's flat. So -1 to 0, union with 0 to 1, and of course decreasing outside of there. Let me stop for a minute. All right. Then this guy, I basically showed you. Did anyone have any trouble with that? Anybody get that far? Okay. What are the critical numbers for the second derivative? Yeah, 0 for sure.
And then I got the square root of -1/2.
Well, square root of +1/2 because you would add the -2x squared, or you could subtract 1 and then divide by -2.
Oh,
So
by 2.
yeah.
Yeah. I just
So it kind of looks like
square root of 1/2.
trigonometry. Yes. 1 over square root of 2, which could make rad 2 over 2, but who gives a shit? All right, let me stop for a minute. Is that right? All right, so now we can make a sign diagram to investigate these things. What's the multiplicity of each one of these where they came from? Can you guys factor this? Can you guys factor that? Anybody?
No.
1 minus rad 2x, 1 plus rad 2x. Right? Because how does difference of squares work? Take square root of everything. So what do you normally focus on when you first learn it? Numbers that will stay whole. But who gives, math doesn't give a shit if it's whole or not. We just do because we're humans. We don't like rad 2, but okay, I don't know if you guys are with me or not on that. What's the multiplicity on each one? Yes? So each one, it's going to go through. It's going to change sign. Do you have to actually do it that way? No, you never have to think about multiplicity. You could just investigate everywhere. You put my other stuff down here. What time is it? Jeebus. So if I put in here like 5, positive, positive, negative, yes? So it looks like it's going to be negative up here, and then it's going to change sign everywhere because they were all multiplicity. One, if you don't want to do multiplicity, you could just check each region. You could just plug a number in. Have fun with finding a number between there that you want to work with. So this is why I really try to push multiplicity on you, because it makes this so much quicker. All right, so what does this mean? Where does it concave up? From what to what?
Infinity to 0.
Negative infinity to what?
0.
No. Yeah, negative 1 over rad 2, because then it becomes concave down here, right?
I guess.
What do you mean, yes? So concave up means the second derivative is positive, the same way that increasing means the first derivative is positive. So if the second derivative is negative, that's concave down. Yeah. So where else is it concave up? From 0 to 1 over square root of 2, and then where's it concave down? Negative 1 over square root of 2, 0, and 1 over square root of 2 to infinity. Okay. Are there inflection points? Yes. One of them is at negative 1 over square root of 2, comma, oh shit! This is where you just throw them in the old calculator. Right, because you got to put them in here, yes? Because again, and I think you guys can see this, where do you plug the thing you're looking at right now? That's going to be a continuous problem. We've got to be careful. So right now I want to know the actual points. I got to plug it into the actual function. So that's just going to be some gross thing. And then the other one will be at 1 over square root of 2. Up 0. Don't forget that. Jeff, make it a point, dude. 0 something. And then 1 over square root of 2 something. Oh boy. So we got 3 inflection points. Oh, jeebus. So I don't know. Somebody help me out. Can somebody plug that in there? What do you guys think? You guys want to finish this up next time? I don't want to try to cram this all in right now. Or do you guys want to keep going? It's up to you. Keep going? I love it. That's what I heard. Ha ha ha. So what do you get when you plug negative 1 over rad 2 into this equation? 1.2374. 1.2374? Does that sound good to everybody else? That's the positive one? What's that? Yeah, so I get, yeah, I get 1.2374 for the positive one. I think that's what you said, 1.23 or for 1.24, and then negative 1.24 for the other one. And 0 is 0. It's amazing. Okay. All right, so watch this. Okay, here's where we got a lot more stuff happening. Here's the magic of this. If you just label things, it will almost draw itself. Okay. So I've got, let's see, let's gather everything together. I've got 0. What are my intercepts, first off? How do I factor this thing? I got some nifty stuff here. So my intercepts are 0, 0. And square root of 5/3. Yes?
Yeah.
And let's see. Negative square root of 5/3. So what's the square root of 5/3? Yeah, so it'll be 1.290 and negative 1.290. So I got 0, 0. All right. This is why I want to kind of do, let's see. Oh, we got so many things happening so close. This is why I wanted to do this problem, because you guys can be nice to yourself with your scale. Look how everything is happening within -1 to 1, basically, right? This one is -1.24. 1.24 is 1.29, -1.29. So maybe I want to make each one of these, let's see. Well, if I do 0.25, I need to be able to get on the other side of 1, right? So at least I could do 0.5 would be a little bit better. -0.5, -1, -1.5, -2, -2.5. So I'll tell you what, go ahead and try to finish that. I'm not going to try to finish that. We'll do this very first thing next time on Wednesday. We'll finish this up. Okay? But the huge thing is, if you label, when you put a point down, if you label it, when you start to go across, you just, if it says minimum, you know to turn around from it. If it says maximum, if it says inflection point, you know you got to change the concavity there. So we'll do that next time. All right. Let me know if you guys have any questions.